Now sometimes we're given a differential equation that is not exact, but if we can come up with a clever integrating factor, it will turn it into an exact equation. And so the way we can test that is accordingly. If my minus nx over n is just a function of x alone, then we can have an integrating factor mu of x equals e to the integral of my minus nx over n dx. If nx minus my over m is just a function of y, then we have an integrating factor of e to the integral nx minus my over m dy. When this happens, if you multiply in your integrating factor, the result is an exact equation. I'll show you an example of this on the computer. Now that we have the computer up and going, I'm going to show you an example of solving a non-exact equation by turning it into an exact equation. And this doesn't always work, but hopefully it'll work when we need it. So here we have cosine x dx plus 1 plus 2 over y sine x dy equals 0. This is our example. And so we're suspicious that maybe this isn't exact. So we're going to test to see if it's exact or not. So I'll say test for exactness. And so remember the way you do that is by checking out the partial derivatives. So cosine x here is what I mean by mxy, and this 1 plus 2 over y sine x is what I mean by nxy. So for my test, I need to check the partial derivative of m with respect to y, but since cosine x is just a function of x, it's a constant, its derivative with respect to y would be 0. Now I take the derivative of n with respect to x. The 1 plus 2y is all constant. So the only thing I have to consider then is the sine x. So I have 1 plus 2 over y times the derivative of sine x with respect to x, which is cosine x. Now clearly these are not the same thing. So this is not an exact equation. Alright, so from there, hopefully we can decide upon some sort of substitution or an integration factor that if I multiply it in, it'll turn this into an exact equation. And so we saw our criterion on the board. And what I notice here is if I take nx minus my divided by m, that is the 1 plus 2 over y cosine x minus 0 divided by cosine x, that gives me 1 plus 2 over y, which is strictly some sort of function for y. So then that tells me that I have an integrating factor mu y, which is e to the integral power of that expression, nx minus my over m dy. So that's going to be the integral e to the integral 1 plus 2 over y dy, which then is integrating, and the integral of 1 is y, and the integral of 2 over y would be 2 ln y. Okay, so now I need to make sure I'm good with my exponents here. That's going to be e to the y times e to the 2 ln y. And using property of logarithms, I can say that's e to the ln y squared. And so I end up with an integrating factor of y squared e to the y. So now I have my integrating factor. y squared e to the y. I take my exact equation and multiply everything in my equation by this term. So now I'm dealing with the differential equation. So now I have my integrating factor, y squared e to the y. And when I multiply this integrating factor across everything in my original equation, the result will be exact. So my new equation then is y squared e to the y cosine x dx plus y squared e to the y times 1 plus 2 over y sine x dy equals 0. And it may help if I clean this up a little bit. So I'm going to have y squared e to the y cosine x dx plus y squared e to the y sine x plus y to the first power times 2 e to the y sine x, and all of that dy equals 0. So now this is an exact equation, and we know how to solve it. And in fact, I will show you how to solve this. Okay, so we take this equation, and again I'm going to multiply in my integrating factor. So I have y squared e to the y cosine x dx plus y squared e to the y plus 2y e to the y. This time I'm going to take out the sine x dy equals 0. So now remember, the idea is since this is an exact equation, there is some function f whose differential looks like this thing. And in particular, if I take that function f and take its partial derivative with respect to x, I end up with this y squared e to the y cosine x. So then my f of xy equals the integral of y squared e to the y cosine x dx, which is y squared e to the y sine x plus some sort of constant of integration, which is a function of y. Now to figure out what this constant of integration is, I take the partial derivative of this f with respect to y and compare it to my known value of n. And n is all of this right here. Okay, so now let's take the partial of this guy with respect to y. And you'll want to be a little careful here. We're going to have to use chain rule. And I think it's easiest, since the sine x is a function of x, we could factor it out as a constant. And I think that makes our work a little easier. So I'm going to take out the sine x, and now I'll just take the derivative of y squared e to the y with respect to y. So I need to use product rule. That's going to be the first, which is y squared, times the derivative of the second, which is e to the y, plus the second, which is e to the y, times the derivative of the first, which is 2y. And then, of course, I have the derivative g prime of y. Now, this is supposed to be n. So I compare it to my n up here. And I notice I have sine x times y squared e to the y plus 2y e to the y, which is exactly what I have down here. So there's actually nothing there for my g prime. So g prime in this case equals 0, which implies that my g would just have to be some sort of constant. So that means that my function, whose differential looks like this equation, is some function f of xy equals a constant, and that function is exactly what we found, y squared e to the y sine x equals c. Alright, now I appreciate you listening. Hopefully this answered some questions. If you do have some questions, leave them in the comments and I'd be glad to help. Thank you.